That date is wrong because that's from last week. Okay, so can I get a show of hands who was here last week? Okay, who wasn't here last week? Okay, out of the people who weren't here last week, what's the comfortable level of type theory? What? Okay. Oh, I mean that's enough. Okay, should I do a super quick run through of just what we covered last week?
I would recommend it.
Okay, all right. Well, we'll do a very quick. Okay. So what we went through last week, we covered everything minus one thing of Martin-Löf type theory, and in particular, that means we went through. This is an example of an inductive type. An inductive type is a. I'm going to assume that anyone who wasn't here at least has an idea of what a type was, because we can't go through that again. An inductive type is a type that is made via constructors, and because it's made via constructors, what that means is when I say that a thing is in a type, I'm not saying that it's like a set membership statement. I'm not asking a falsifiable, is this in the type or isn't it? I'm saying that this thing, whatever I'm pointing to, I'm saying that it exists because it's in the type. And what that means also is that I know what's in it because I know how that type is made. So this is the example type that we went through, or the option type. An option type has two constructors. It's either none or it contains some bit of data. And because I know that these are the two constructors, anytime I'm given an option type, I look at that thing that I'm given in the option type and I say, okay, well, what is it? I know it has to be only one of those two, right? And this abstracts to larger numbers of constructors that have different fields and different arguments. And what that means is that no matter what inductive type I'm given, no matter what I am given in the inductive type, I always know how it is made, right? And we went from there to introducing some notable examples. Here's one. The pair type, which is just, it makes a pair out of 2 bits of data from 2 different types. And it has 2 notable destructors. In particular, you can project out the first item in the pair, or you can project out the second item in the pair and throw the other one away. And then we also had the sum type, which is notable because it's sort of like a flipped version of the pair type, where you say, I have 2 types, and instead of taking 2 bits of data, 1 from each type, I'm going to take 1 bit of data, and I don't care which type it's from, right? So I have 2 constructors, but which kind of data the constructor is actually holding is ambiguous, right? When I have a sum type, I say, all right, well, maybe I have something from type X, maybe I have something from type Y. I don't know. All I know is I'm going to get one of them, and I know what to do if I get one or the other. And then we got to proposition types, and proposition types are basically you just say that like a type or a proposition can be thought of as a type, and it is said to be true when it is inhabited, when it has something in it, right? When you say that I can make a thing in that type. So the way to say that a thing is trivially just true, like a true statement, we have the true type. It has 1 constructor called star. That's just what people tend to call it. And then when you have a type that is false, and the sort of like archetypal false type has 0 constructors, right? So anytime I have a function that wants to take false as an argument or produce false as an output, when I have that false value, I say, okay, how did you make this false value? Okay, well, you can't make false values, which means that whatever case that I'm encountering where how did I get this false value, I know when I'm writing the function that just didn't happen, right? Using that and using the things we mentioned earlier, we had the basic sort of logical operations. We can do a logical AND by saying if I have 2 proposition types and I want to make a new proposition type that only has something in it, if both of these 2 proposition types are inhabited, then I just take 1 from each and I make a pair. I can't make that pair unless I have a bit of data from both of those types, right? Does that make sense to everyone? Okay. For the OR, logical OR, I say, okay, I'm going to take sum type, and that means that I can make this sum type. I can make something in this sum type if I can find something in either of these 2 types, right? And because of that, then I can construct a proof of the OR statement if I have a proof of either, right? I forgot this last time as well. If you haven't encountered this before, The proof in a proposition type, it can be called a proof. It's also usually called a witness or an evidence, right? Implication is just a function. If you have a function from type P to type Q, and these are proposition types, then you can prove Q if you have P because you just run the function on it. Negation type. If you have an empty type, right, a function has to assign an output to every input, right? If I say that the input is the empty type, I have no obligations in defining a function. So the proof is defined immediately. This is the same thing as the principle of explosion, which is if false, then anything, and that follows just because, I have a mapping out of false. There's nothing to map. I'm done. My obligations are fulfilled. I have a function. The reverse is also interesting, which is that if your output is false, then you can't find any outputs to assign to any inputs unless you have no inputs. So when you say I have the type P to the empty type, this only has a proof if P is itself empty. And so a proof of this ends up being a proof that P is empty. So you can make a logical negation using this. And then you can do proofs as functions in the very straightforward trivial sense, where you just have like literally a function where your inputs are proofs of things, and then you run functions in code or match statements on them. So this is an example of a proof written in Rust. And I think this is technically like zeroth order logic, though, so it's not particularly sophisticated. In order to get, and here's the same thing in Haskell, if anyone's more inclined to that. We have dependent types, which allow us to say more complex statements, such as a condition, which may only be true on particular elements of a type. So if we have the natural number type, the counting numbers, not every counting number is even. But if you have the question, is this number even? That is a proposition, and it is a different proposition from a different proposition that says, is 5 even versus 3 even, right? Those are two different propositions, but they both take a natural number and make a type, right? So that kind of a condition, we call that a type family. And using a type family, you can say, you can make a dependent function, which is a function where the output type changes depending on the individual element of the input type, right? So if I had, for some reason, a proof of for all n is even, which of course doesn't make sense, but let's say for a moment I did, I would have a function that can take n and, as a function, produce a proof or a witness that n is even. And then we also have dependent pairs, which acts as our there exists type, where you say, if I can make a pair where I have the element itself, like a number, n, and I can find a proof of a proposition about that, say, is n even, then I know that there is at least one natural number that is even, right? Okay, so if that didn't make sense to you, it's because I skipped through it very, very fast, because we covered this last week. But basically, we have a correspondence between all of the logical operations you might want, true, false, and, or, for all, there exists, and implies, and different things that you find in type theory, the unit type, the empty type, the product type, the sum type. We call this the pi type for the dependent functions, and the sigma type for dependent pairs. And you can also, using those tools, build bidirectional implication. And there's one thing missing here to build up a Martin-Love type theory, and we'll get to that in a few minutes. Okay, now that we have that, we can get to the actual thing that I wanted to do, which is, okay, let's get the theme. Preferences. Oh, for God's sake. Okay, can everyone see this properly?
Yeah, that's better.
Okay. All right, so Rado was very kind to take the example Agda code I put together and convert it, in a manner of speaking, to Lean. So we have a sort of correspondence for what we're going to do here. But first, I just want to point to the corresponding things that I mentioned in the last couple of minutes. We have the empty type. We have the true type with the one constructor star. No constructors for data, you see, or for empty, rather. We have the binary sum type and an alias to make it look pretty. It looks like we call that dot plus. we have the negation type. Now the negation type is also written here as a type alias. That will fix itself in a moment. Let's do that. Okay. Okay. Now, a moment ago, I showed you this proof. Actually, we'll do the Haskell version for here. Now, this is a proof of the statement. If P or Q and not P, then Q. Does that make sense to everyone? Okay. So the way that we're going to do that, okay. Let's look at that again. Okay. So the way that we did this is we said, all right, well, let's look inside our proof of P or Q, right? We need to ask, was this P or was this Q? Like, how do we know that P or Q is true? Do we know it's true because it's P or because it's Q? If it's Q, I have my proof of Q. I just say give back the Q, right? The interesting thing I covered last week that I always feel very excited by, I don't know about anyone else, is that when you write your proof as a function like this, when you have an impossible case, when you want to say like, okay, well, you're not supposed to be able to pass a P into this because we have a proof of not P, right? You are not absolved of writing what this function does when it gets a P. The trick is that when it gets a P, you say, okay, well, you're not supposed to have gotten a P. And if you did get a P, then I can run this function, the negation P, on it, which is our G. That G is the proof of negation of P, which, remember, was a proof from P to the empty type. Now I have an element of the empty type. And with an element of the empty type, I can prove anything I want. So I have this trivial function that says prove anything I want if true is true. And for that, I prove Q, right? So I still have to do something in this case. I just do whatever I want because I've proven that false is true, which doesn't make sense. Okay, now we can convert that. And the way that we're going to do this, actually, okay, should we start with the lean version?
Yeah.
Okay, let's start with the lean version because that's familiar to a lot more people here. Okay. Oh, is this already, okay. Did you want to, do we want to do it with tactics? I think tactics might be better.
Yeah.
Oh dear, that's a bit more than I wanted to do. Okay. Okay, buy is how you begin tactics mode, right?
Yeah.
Okay, so, oh, should I? Okay, we have the goal state down the bottom. Can everyone see this? Okay, so we have, what is that? Okay, we have the types P and Q. We have a proof of P or Q, and you see that as H hypothesis in P plus Q, the sum type. And we have a proof of not P, which is called HNP. So, okay, can we, the keyword here would be case, right? Cases of, how do I do this? H. And then, do I tab in like that? That's how that works?
Now you have two goals.
Two goals. How do I specify which goal I'm working on?
I think there's a bar.
Oh. Like that?
No, without the dash. Oh, never mind. Yeah. I don't remember it. It's not.
Does anyone know what the keyword is here?
Well,
You could say case afterwards without the S and then name it in less than in L.
Case.
Try in L.
I know.
Because the cases are names. See?
Oh,
Case
yeah.
and left, case and right.
Does that work? No?
It seemed happier without the parentheses.
It's a situation where I'm just not a lean programmer. This is going to be a lot smoother in Agda.
I think you may want to, I'm not sure that you want to start with cases H. You might want to start with case I and L.
Well, because we're trying to case split on H, right? So that the in INL will be a constructor for it.
All right.
That's a match variable with, right?
What matches for the non-tactics mode? So matches like
Oh,
yeah, that's the trouble.
Yeah, so how do you destruct H?
Yeah, I mean, if this was in COQ, I'd be, right with it.
I mean, it seems like you have two goals, case I
It's
know.
with.
Yeah.
case I
There's
know.
a keyword with.
It what now?
This is with.
With.
Yeah. Now
Okay.
you do.
Like
now
that?
for the constructor, enel. Okay. And
Okay.
now you do fat arrow. Fat arrow
Oh.
equals. Okay. Yeah. Now you're in the first case, and you have P. Yeah.
Okay, and now we can fill these in. All right. So for this case, is it going to be upset? Oh, okay. Hang on.
Yeah,
Can I
it's,
just?
I think it's the bar that's complaining about.
Just start typing something.
Okay.
Maybe buy again.
So in the case of P, remember, what we did is we said we did the negation of it. Can you? What's the? You can.
We have the.
You have H and P to use.
H and P. Okay. If I do H and P H, it's probably going to tell me that I now have a proof of false. Can I, with a proof of false, how do you say that I'm in an absurd case?
False type you live.
Huh?
False type you live.
You need exact if you want to return. Exact is returning tactics. Okay. So now you
No?
don't have H anymore because you struck it.
Oh, right. Hang on. It was
Yeah, P though.
P.
Okay, we're almost there.
Oh,
Okay,
because
yeah.
it doesn't recognize my thing as the false type.
No, it
You
does
just need
recognize
to
the
pass
false
it
type.
into-
We haven't converted it from the false type
Yeah.
to A yet. We haven't used 0 not epilim.
0 on the
0 to 1?
The
Oh,
function on
right,
line
because I have to
50.
use this one. Okay.
Which is
So I assume it's like a
You need
different.
it.
exact as well.
Okay. And then for the other one, we just do exactly what we do normally.
exactly.
Maybe you need exact, I think.
Okay.
And now everybody's convinced not to use tactics. 'Cause it
Yeah,
makes it
yeah,
longer. But
Tactics,
actually, if you're
well,
writing math,
I don't know. I think I like the tactics in COQ quite a lot. But the point of that is to highlight that we're going to do this a bit. Well, actually, in this case, it's not going to look so different just because it's a very simple case. But okay, so Agda inherits a lot from Emacs. And the way that you use Agda to this day is basically pretending you're still using Emacs, even if you're using VS Code. So the key binding that you use is, I shit you not, Control-C and then Control-L, and it's going to turn every question mark into a hole. Now, Agda uses hole-based programming. So what that means is that instead of having like a tactic situation where I remember at the beginning, I hadn't filled in any of this, and it just said, okay, well, you have a goal, right? I'd do this, and I go back here, and it says, you have a goal here that you haven't done anything with. And then I put that back, and, oh, hang on. Is it not happy?
That's happy.
Okay, but it's still saying I have a goal, though.
Your cursor.
You're
Oh,
in the middle.
okay.
You're in the middle of the proof.
Yeah, okay, so and then no goals, right?
Mm-hmm.
So previously, it showed me a goal in Lean. In Agda, we also have goals, but our goals aren't things that we sort of like successively like do lines of operations that transform things like sort of actions on a state, right? You don't have a state in the same way in Agda. You kind of do, but it is principally by the kind of proof you're trying to produce, right? So when I'm saying I'm making this function, square bracket I close square bracket, I'm trying to say, okay, well, if I have this argument little x and this argument not p, then whatever this is that I'm going to put here, it better be of type q. And you see this because this is goal 0, and goal 0 must be a type q, right? So let me go in there, and I say Control-C, Control dot, right? Now this is all the information I have if I'm in that hole, right? I have x, which is of type p or q. I have not p, which is of type not p. And I have q and I have p, but these are implicit, right? I've defined them implicit, you see by the curly braces. So I can't really use them, but that's not like anyone's fault. I could just put them in manually if I wanted to. I could be like p, q, and then these are no longer implicit. They are fully explicit. But I don't have to if they don't matter, right? Okay, so if we're going to go about translating what we did earlier, what we do, so here's where things get interesting. Because it is from Emacs, it inherits also from the tradition of giving you a bunch of like weird tools that you can use. So here's what I'm going to do. First, you see this X. This is an X in P or Q, right? I'd like to destruct on this. I'd like to do the same thing I did here, where I said cases H with, and then I have 2 different cases to work with. I can actually do this in a really nice way, where I say Control C, and it's going to say, would you like to case split on something? And I say, yes, I'd love to case split on X. What's going on? Is it taking it? What did it do?
You created a new file.
I should. Oh, God. Oh. Is Lean fighting it? Hope not. That's weird. What is going on there?
VS Code is sucking.
Yeah. Hang on. Be absolutely sure that I have the language server running.
Would it help if you ran an Emacs?
Well, I would not personally use it. I'm going to try closing this actually, because I'm suspicious that this is part of why that's happening. Never had this error before. There we go. Okay, so I say, yes, I'd love to case split on X. And I press enter, and look at that. It says, okay, here are the 2 versions of X you could get. It could be in left X, in which case it came from P, or in right X, in which case it came from Q. But let's rename those real quick, just because it's a little less obvious in the actual state that's going on. Okay, so I run my Control-C, Control-L. And mind you, you have to Control-C, Control-L a lot every time like something changes, so it knows like, okay, I'm going to reparse things, I'm going to update what's going on, right? So we're now in the goal state of this we're case broken on X, and now we have P, and we have our not P, and we need something of Q, right? This is marked goal.
So the little not P is just a variable name. It's not
Yeah.
destructuring the not. It's just you're naming your.
I've named this. So okay. So something about Agda is you can use all kinds of weird symbols in your variables. You can use square brackets. You can't use normal brackets, but a lot of symbols you can use in your variables. The way that Agda knows that 2 things are not part of the same name is the space, and so you have to use spaces very aggressively. As well as, and I'll get into a second, underscores. Underscores are treated funny. But okay, so if I'm in this goal state, I have this P, and I have, I mentioned earlier that you want to have some kind of trivial function that goes from the empty type to anything. Now I have 2 different versions of this, one that does this in the way that you saw earlier, and one that does it for a dependent type, because I might want to do a empty elimination on some thing that's more complicated than just a non-dependent type. So I do, same thing as Lean, by the way, if you want to do special characters. You do backslash, and then I do B0 to get this fancy 0. 0 elimination. Oh, here's a funny thing. Okay, so I know that I want a proof of Q, and I know that this is going to give me my proof of Q. But what I can do is I can put a question mark in this hole, and then I do Control-C-L just to reload, and then I do Control-C space. And Control-C space, what that's going to do is it's going to say, all right, whatever I put in this hole, I think it's a good thing to put here. And Agda is going to say, yes, this is a good thing to put here, or no, I don't think that you can get away with putting that there. But if it thinks it can get away with putting it there, even with a question mark, it'll say, all right, well, this 0 eliminator, it's a function. It takes something. I don't know how you're going to give this to me, but if you did, this will work. Right? So I've transformed my goal state, not via tactic, but by saying, okay, this is the function that's going to give me the output I want, the witness of the proof that I want. I don't know how I'm going to satisfy that function, but that's what I'm going to do.
So basically, instead of putting the names of tactics into your proof, you're putting keystrokes into your editor, and it's giving you terms.
well, I'm putting functions into the holes. And the functions play a role kind of like tactics, but in reverse in a lot of ways, right? So whereas with a, how do I say this? Tactics, I tend to think of as allowing you to approach a problem from the end and from the beginning at the same time. You can build up statements, usually by like apply this, have that, as well as transforming your goal state, right? You can transform your goal state here, but only up to a point, because what you're doing is you're saying like, okay, well, at some point in the future, I will satisfy this function, right? But the actual, like, you are building a function, right? At the end of the day, you look at that function, you say, okay, that transforms not a goal state really, but like it just takes inputs and does things with them, right? You can always see the control flow of the proof. Okay, now if I do Control C, Control dot again. All right, this knows that it's going to give me something, but it doesn't actually know what that something is other than it ought to be Q. So it also doesn't know what it's going to take other than, oh, it needs to take an empty type. For that, let's just do the same trick I did again. Neg P, that is a function, and I'm going to say, all right, well, I don't know how I'm going to satisfy that, but I'm going to do it anyway. I do that, go back into my goal state. Now I need something of P, and I have that thing of P, and I'm going to do Control C, Control A for auto, and it's going to say, I know what to put there, right? So the interesting thing about this is that unlike languages like COQ or Lean, when you say something like auto, that doesn't mean try to see if you can figure out how to prove this and then do that every time you like check it. It means if you believe you can autofill this, you are actually going to put the code there that satisfies the function. So that auto is not actually going to help you very often. It's mostly like you are 5 keystrokes away from actually solving the thing. But it does mean that you're always going to actually have a thing that, as I said earlier, you can trace the control flow, right? It's never mysterious. So, okay, let's finish the rest of this proof. We have the.
If you have a type error,
yes?
do you still have to do the Emacs thing or to do a red squiggly?
A type error in here?
Yeah.
Okay, so here, I'm glad you asked. If I say neg P, and I do Control C, Control dot, right? It's going to tell me, you need this. That's what you have, though, right? You need something in type Q. Currently, you've given me something in type not P, right? So if I then do Control C, Control space to try to give it to the whole, it's going to say, you can't do that. But it's also not going to change anything, right? So it's not broken. It's not bonked. It's not like type error, fix your code. It's literally just like, I'm just not going to let you put that there.
But if you're outside of whole.
Oh yeah. So if you negative P.
It's just it's not live updating like Lean.
No, so you update by doing Control C, Control L, right?
Yeah,
and if I did this now, it's going to say, I don't know what to do with this. Now it's bonked the code because it's not in the hole to make it safe, right? If I do that, it's safe. I say, all right, well, I'll give you I'll just do Control C, Control A. It gives the Q because it has a Q to give. We're done, all right? So let me move this over a little bit. All right, we're going to do that again, but this time I want to demonstrate the infix notation. So I mentioned that variable names were very forgiving with symbols. Like I have minus signs in this variable name, and those minus signs don't do anything. They're literally just hyphens, right? But these underscores are places an argument could go, right? So previously, I was doing the elimination on the sum type by saying, I'm just going to do Control C, Control C. I want a case split on this variable, but I can do it a different way. I can say, all right, let's have the eliminator as a function, right? It looks like an if, then, or else. And what we're going to do is we're going to say, okay, well, let's define this explicitly. We'll Control C, Control, all right. All right, proof is, or not proof, goal is something in type R, right? Now, we actually do want this to act like a function in this case. So let's split on X. And I promise with the next one, I will actually start getting the crowd to solve this via telling me what to do. But okay, we Control C to split on X. Now we're in the 2 different cases of X, and we can literally just say, if it is P, actually let's rename these. If P, run F, and if Q, run G, right? So now we have a way to break the cases on some sum type by giving it a function that says, okay, this is what you do in this case, this is what you do in that case, and now it looks like a weird if, then, else statement, right? And the way that plays out, if I'm going to use that there, is I say, okay, if question mark left question mark, but if right question mark, control C, control L, control C, control space.
What the underscores do in the
Sorry?
name?
Oh, the underscores, they specify where arguments can go,
Yeah.
right? So you might have seen earlier.
Okay, now that makes sense.
Yeah. So that plus, I defined that using the underscores to make an infix, right? Same thing with that one. But you can do them in really crazy ways, which is the point of that example, right? You can put them,
Constructor split between three different keywords.
right?
If,
You,
left, and
you can make really complicated like sentences that are just like functions with infix things going on. Okay. And then for this one, I would literally just use this the way that I did above. Although for the F and G, I do need a function. So lambda, say P to question mark, and lambda Q to question mark. And of course, this one, it's just Q to Q because that's what we did here. And this one, we had to do that. So let's do that. So same thing, but we've just used the infix notation to very aggressively make it look like a sentence in a manner of speaking. But okay, all right, I'm going to start prompting everyone else now. So we're gonna solve this together, I guess. Okay, if I give you this statement, so bearing in mind what I said earlier about how you read types as propositions, this is first A and B or C implies A or C and B or C, right? Can we, all right, never minding the type system for a moment there, why do we think this should be true? Can we convince ourselves of this? Right? Sure, go ahead.
Well, you're given either an A or B.
Or an A and a B, yeah.
B or a C.
Yes. So what do I do in either cases, right?
So if you have a C, you can just create both on the right-hand side.
Yeah, so I have a C in this case, and I have a C in that case, yeah.
And if you have A and XB, you just do the same kind of thing.
Yeah, so I put A in there and I put B in there, right? Okay, how am I going to do this as code, right? So I get as an argument X in, it's either a pair AB or it's in C. What should I do?
Match.
Match, okay, so case split. All right, we do control C, match on X. Okay, this is the state we're in now. Now our X is in type A or B, or sorry, A and B, rather, at least for the first goal. All right, what do we do? Sure?
Create a pair.
Yeah, okay, so
You need to return X.
go ahead.
Oh, yeah. Construct a tuple with the arguments and X taken apart.
Yeah, so if I do, this will work? Yeah, okay, that's a weird way to do that. But let's just rename those. Okay, so now we have A and B, and we need to construct this A or C times, or and B or C. And it's gotten rid of the parentheses, but that's fine. We just, oh, hang on, that won't work. We need in left A, in left B, and let's see, is that correct?
Space.
Yes, you are right.
You foreshadowed.
Yeah, no, it's a recurrent problem. Okay.
It thought the comma was part of the identifier.
Symbols are
Yeah, well, if you can see here as well, I put an apostrophe in this variable name. That's still a variable, right? You
Sure,
can
that's
go,
so you can do that in Lean.
really?
Apostrophe, but
Yeah.
not a comma.
And Haskell too.
Yeah.
Probably not the square.
Also OCaml.
But,
Yeah,
but they're,
well-
they're more reserved. Supposed to be.
Let me show you how the comma is defined, which is a bit on the ugly side. But the way that you build this up, if you want to do it in the way that we're working with it right now, is that because pairs, like you want to use the same syntax for pairs as you do for like dependent pairs, which means that you make dependent pairs first, and then you say that normal pairs are a special case where it's a dependent pair, but the second type just happens to not depend on anything. So then the comma is literally an operator in the way that you saw earlier.
Right.
Let's go back. Okay. Okay. This one, all right, let's get rid of that actually, and then let's solve this ourselves. Okay. All right, this statement, not A or B, implies not A and not B. Does everyone agree with this? Right, this makes sense? All right, if not A or B, then not A and not B. How are we gonna do this? Let's look at what we have. That's what we need. This is what we have. What should we do? Nothing. We need to make a pair, right? Should we make a
We
pair?
need to show that we can't make a pair.
Well, no. Okay, so we have a pair of two nots,
Oh,
right?
okay.
So you can see we have not A and not B. So let's make a pair.
So I guess the first element of the pair is a not elimination on A, and the second is a not elimination on B. But we only have that if we know that A and B are empty.
Well, okay, so we need not A. We have not A or B, right?
So we can turn our not in, I don't know.
Write a lambda.
Like we write the not map for poles, and maybe try to use something with the if left but if right elimination rule.
Yeah,
So
okay.
they distribute out the not.
So remember, this is a function, right? It takes A or B. Can we make A or B? Can we make A or B?
Prove not A. We take A, and then we can make A or B, and then we prove.
Okay, so
Should we write a lambda
yeah, let's make a lambda.
to get an
Right, because we need A to not, or A to empty. We do this. All right, do we have A or B?
A?
Yeah, okay. So let's put our A in there. Okay. All right, we're gonna get empty. We're gonna get empty from this, because remember, this is A or B to empty. So we do F question mark. Control C, control space. Let's do it. Okay, we have A. We need A or B. We do in left A. Okay, that part's done. All right, now we're going to do the same thing basically.
Right B.
Sorry?
Oh, like
Yeah.
you know, syntax fun B to arrow F of the in right of B. In that order.
Right. Yeah. Yeah. Okay. All right, now we're going to do something that, if this is a sort of rough statement of contrapositive. Does everyone recognize this? Right? A implies B, and not B implies not A. So let's do this one. So we have our, let's do Control C, dot. We have not B, we have F, we need not A. Okay, So remember, not A is a function A to empty, right? So let's fulfill our obligation there. We're going to say, all right, well, let's assume that I'm given an A. So here's actually a funny thing I should point out. Do you remember last time I said that this arrow is right associative, right? So what do you think right associativity does when it sees in here that that is a function type? This is going to look really unintuitive. I don't need to put a lambda A here. I can put the A here. Right? Now I have that A, but my goal is no longer not A, it is empty type. Okay, so now we need to do that. We don't need to do little lambda there. You could do little lambda to all kinds of levels. We could like take these arguments out and say like lambda F not B A, but not necessary. But for exactly the same reason that we can put the A there, right? We could have put lambda A2, or we put A on the other side. So okay, we need an empty type. We have one way to get that empty type is with this, right? Because that's a not B. So
And we have an A.
yeah, we have an A. Let's do that. Okay. So now now we have our goal state B. We still have that. We have this. Should we use this?
Let's use that. Let's apply it to our A.
Okay, let's apply it to our A. Control C, Control dot. Goal is B, have B, we can give it. And we do that, and it says that's the proof. Does everyone see what's going on here, right? Like, these are literally just functions, like, to the fullest extent. We are passing around bits of proof evidence.
This is fucking mind-bending.
What now?
I said this is fucking mind-bending.
Is it? I hope so. It was mind-bending for me the first time. And then after this, I can't help but see this. I look at Lean, I look at COQ, I look at any other like language. I think this is happening under the hood, and it's not what's always happening under the hood, which is, but it feels like it should be once you see it.
Is there an association going on the left-hand side of the equal sign in line 4? In other words, is not B associated with A, or is it F?
Sorry,
not B?
line 4?
Line Roman numeral 4.
Line 57.
This one, okay.
Line 57.
What was the question?
Is there an association going on the left-hand side of the equal sign?
No. No.
I mean, yes, it's left associative.
It's
the function application is left associative.
Yeah. So you should think.
Right, but what is the function? Is the function only F, or is the function F of not B, or is the function F of not B of A?
All of those are functions.
Okay.
So for 4 of F is a function, 4 of F applied to not B is a function.
Oh.
4 of
4 is a function.
So.
Yeah.
Oh.
Right, that's
So-
the function we're
So
defining
that's what I mentioned earlier, that like you can get very liberal with which symbols are put in the function, right? So this is
Alright.
one you can use. You can have like this weird infix thing going on. You have function 1, like square bracket I close square bracket.
Okay.
That's a function. This is a function
Alright.
with the apostrophe in it. There's a lot you can do.
I didn't expect that 4th was going to be good preparation for Agda.
The what now?
That 4th was going to be good preparation for Agda.
Oh.
The syntax of 4th is words are separated by spaces. That's the whole syntax.
Oh. Well, it can be. Like I said, so that's
I mean,
just
here you have parentheses as well.
Yeah. Well,
Right.
but it's a choice, right? You could have it look very horrible like this, or you can make it look like that, and there's no reason you can't do either, right? Or you can mix them if you want to. The infix gives you a lot of options. Mind you, also you could get a lot more aggressive with that infix because Agda supports.
I was wondering if you actually needed those parentheses in the around the argument of your first argument.
Yeah. So
Your second argument of if left, but if because you have parens around your lambda there, but are those actually needed? The parens?
well, let me show you something. If I do that, and I do this. If this left fs, but if right. Actually, hang on. I don't need the s there. And this should, I think, yeah. So you can use the let in binding to
Sure,
literally
sure.
just move things around, and any clunkiness that you make it fully look like a worded statement if you want to do that. There's also where. I know that a lot of languages that have let in also have where, and same thing here. Where can be a lot nicer. In Haskell, when I do Haskell, I prefer let in. Previously, when I've done a lot of Agda, use where a lot. Okay, let's do.
Can we do a time check?
Yes.
We have like 5 files. So is there?
Okay. Well, okay, we don't have to spend equal attention on things, but let me skip ahead a little bit. So because there is something I should show you. Okay, this one standard. Oh, what's wrong? Oh, it's because I.
might have messed up.
No, this is my copy. There we go. So here we can do a proof of induction. Mind you, the proof for natural number induction is actually a thing you have to provide yourself, the same way that we had empty elimination before. Let's come back to this actually, but I want to show you this because this is the thing that is going to trip you up if you haven't seen it before, and this is also the last bit of the Martin-Love type theory. Okay, so here is our inductive constructor for the notion of equivalence, right? Again, inductive, right? The value of this is that anytime I have a function that needs to take equivalence as a proof, the way that equivalence works is that you say, by inductive construction, there is only one way you could have run this function, and only one kind, in this case, one kind of type evidence you could have given to say that these two things are equal. How do you say that two things are equal? In this case, you say that they are literally the same thing, right? There is the equivalence data constructor constructs the type of A equals A, given, or two things from A, right? So this could be X equals Y, right? But the way that you actually make that proof of X equals Y is you say, okay, well, how would I prove X equals Y? Oh, there's only one way, and it is exactly when Y is X, right? So this leads to a bunch of weird things about the way that you prove things, right? So if I say, let's look in here. I need let's specify these exactly. Let's make these X, Y, and then let's call that P. Okay, if I say, what is that? What on earth is it doing? I gave it the Y. Oh, because it wants A. Okay, so in this case, I say, all right, I've specified these implicit arguments, and you don't have to. Anytime you give it an equivalence, it'll flip the equivalence around for you. But first, we actually have to prove that you can flip an equivalence around, right? How you do this is really interesting, because you have your proof of P, right? And you say, okay, well, it's funny that you say that I have a proof of P when I run this, right? Can I case split on this? And you think, well, case splitting on equivalence? But I can, because it's an inductive type. Right? Inductive types have only so many constructors. And you say, okay, well, you claim when you run the proof of the symmetry of equivalence that you have given me a bit of equivalence, right? A witness to X equals Y. And I ask you, how did you do that? The answer is, you told me that Y is X, right? I put that in there, and assuming nothing breaks, what have I done? Okay, now my proof of P is, oh, actually, this is a situation where it's not so good that I gave it the explicit arguments. I tell it, all right, well, case split on P, or on the proof of X equals Y. What I get back is that the only thing that could have happened here is that Y is X. And if Y is X, I just give it back what it gave me. Goal, X equals X, have X equals X. I give that works. Okay, transitivity.
So that's just an identity function.
Yeah, essentially it's an identity function. But it's an identity function for a really weird reason. Can everyone see what's going on there? No? Okay. So what we've said, right, is that we need to prove that if we can prove x equals y, then we can prove y equals x, right? How do we make a proof of x equals y? Assuming we have. There's only one way. Why not?
By saying returning the thing we already have, since you said assuming we already have.
Yeah, assuming, well, no, okay, sure, okay, we have that, right? How did we get that? How would it have happened that I was provided a proof of x equals y? Under what circumstances does that happen?
If either x is equal to x, or the thing that constructed it was equal to the thing that constructed it.
I'm not sure I follow with that wording. Do you want to?
So the type of the thing. So you have a constructor.
Yeah, I have a constructor for the type constructor, or the constructor for the
For the equality.
Yeah.
Or for the equivalence.
Yeah.
So you have the constructor for the equivalence.
Yeah.
So
Reflexivity.
if you have x is equivalent to y, then it has to be, from that type, it has to be something of the form REFL of something from type, from the A type.
Oh, for reference, if anyone doesn't know this, that REFL is short for reflexivity, right? So you're saying that, like, when you are saying that a relation is equivalence, that always means that thing can be equal to itself, right? And yeah, what we're saying here is that the only way that you prove that one thing is equal to another thing, modulo other theorems that you can get to later, is literally by saying those things always were the same thing, right? So the only way that you get x equals y, or proof of x equals y, is if y was x all along, right? So we get to here and we say, all right, let's turn that back to what it was before, right? I say, okay, well, you claim you gave me a proof of x equals y when you run this function symmetry, which is able to swap an x equals y to a y equals x. I ask you, once again, how did you get that p? So I k-split on p. What do I get? P could only have been reflexivity. That's the only way you could ever get a p like that, right? So I go back and I say, all right, well then, if x is y the whole time, all I need to do is just give it the x equals x proof. And I do that, and that's what you do, right? So, all right, let's do another example of this using reflex.
About that one.
Yeah?
Can you write sim p equals p?
What do you mean?
Like right now, like for
Let-
line 14.
Oh, okay. Let's give that a shot. I don't actually know off the top of my head. No, it doesn't like that.
Right, so like it doesn't unify.
Nah, it can't.
those.
You actually do have to destruct on P. Because until you give it some indication that y has to be x, it looks at that and says x equals y and y equals x are different types, right? But look at this. If I say, let's go back to this point where we had,
Do you know if Haskell would allow sim p equals p in a similar situation?
so here's the thing. Haskell will not allow you to do this, right? Like obviously having a constructor, that's fine. But what's going on here is I'm generating a type family via 2 arguments to this, right? So this is a type x equals y. X equals y are not types themselves. They are elements of a type A, right? That is a dependent function constructor, and you can't do that in Haskell. Haskell just doesn't support dependent types. Okay, if I go here, now I'm going to do something I haven't shown you so far, and I'm going to say Control-C, Control equals. Okay, that might be a thing for later. Okay, so it doesn't believe that there are any constraints. What it does believe is that there is no y. There's just x and x.
There is no spoon.
Okay. All right, let's do this one, for example. Doing it a different way may sort of drive this home. Okay, so I say I have a proof of x equals y, and a proof of y equals z, and I need a proof of x equals z, right? Let's case break on p, right? And I say, okay, well, how could you have possibly given me x equals y of course, the only way is if y was x all along, right? So I do that. What's it done? Okay. Now, what this has done, by saying that x equals y had to be x equals x all along, I've now turned this into x equals z. You see, because y had to be x, right? But if y had to be x, I need to prove x equals z, and I have a proof of x equals z. So I just put that in there. And I'm done.
It's like that always has been the
Yeah. Yeah, it's standing on the moon and, always was.
For sake of time, can we like put a official end and then we can
Yeah.
continue, obviously, but I also want to discuss a little bit what we're going to talk about next time.
All right, then closing statement. Okay, so earlier I showed you this slide, and I titled it Martin Law of Type Theory, Language for Propositions. This has one thing missing from it, and that one thing is the equivalence type I just showed you. This plus the equivalent type is generally what people refer to as Martin Law of Type Theory. I've heard it is very difficult to implement it faithfully as a language, and Agda is kind of like a best effort attempt at that. But things like COQ are built out of, if we can't do this formally, then let's do other things formally. Agda has some issues, but it basically models this in the language. This plus the equivalence you just saw. But those are the core things. You understand that, you can look at other proof-assistant languages and say, I see what that is morally trying to do under the hood, right? But that's the core of it. Thank you for coming, and thank you for listening.
Any quick questions?
Later.
Go ahead.
In that last thing you were doing, transitivity.
Yeah.
What happens if you have to get a case split on Q?
I can do that.
Right. Well, first on P. First case split on P.
Sorry, hang on.
First case split on P as you have done before.
Yeah. And then case split on Q. It's invented a new symbol, and it now believes it has. Yeah. All right. We can go through this a bit more afterwards. Okay. Any high level questions?
I guess.
Oh.
I just want to ask. So I think this style of proving which you have in Agda, I believe is possible to do with, a very similar style of proving in Lean if you just choose to not use tactics and use sorries.
Oh yeah.
Does that match your understanding?
It's definitely closer. Although once you can chase that hole down and you find out that there are deeper parts of the language of Lean that are just completely different from Agda. But yes, there is a strong sense in which the tactics are really just a syntax transformation. And here the syntax transformation is mostly you just have holes, right?
Yeah.
That's the interesting thing there.
What is that deeper part of the language that differs?
Computational quotients, a number of things to do with the way that you do transformations. So in Lean and COQ, you have rewrites. In Agda, the only rewrite that actually occurs is when you execute a function. So the example I would have demonstrated for this is the addition rule. Says, okay, if the first argument is 0 and the second argument is y, I just give back y. If the first argument is something plus 1, because you're case breaking on the first argument, right? Change the plus 1 to the x plus y, and then you can iteratively go down. When you do this in a proof, what it will do is every time you have an equivalence type and it needs to say, is the thing on the left equal to the thing on the right? If it sees a plus, it will try to run that plus one time. And then you have to chain transitivities, and that's how you get that.
Okay.
But you don't have rewrites in the same way you'd think of Lean, this equals that, replace all symbols. Okay, thank you. Sorry for running over time.